Okay, now 3.4, the other part of this, we have to find zeros of functions again like we had done in 3.3, etc. But we're dealing with complex zeros at this point sometimes, and so you just got to know what you're looking for. It just means that essentially some of the zeros you're looking for, they don't show up on a graph. Like we talked about zeros initially of like, here's your graph paper, or whatever, and every time the function crosses the line at the x-intercept is what we call zeros of the functions, or it's whatever x values I could plug in that would make this polynomial function equal out to 0. And that's fine, but there's these are what, sorry for hesitating so much, these are the ones that we see when those are what we call real valued or real number zeros. And so one issue to consider is, remember, when we have a quadratic, like when we have y equals x squared type stuff, they always do the, UE thing. They do the parabola mess, and we know that to look for two different solutions. But if I had, say, even a simple one like y equals x squared plus 5, you know that starts out here, up 5. And then it's like it goes up and out. And you'll notice that although we're supposed to have two zeros here, this thing never actually hits the x-axis. It's not like that one that hits once and twice like we would expect. It doesn't even hit ever. And so you're like, well, this is a problem. And that's where we have some theorems about these things. But I guess the simple take on it for now would be just to say that if it doesn't hit, it means that there are solutions to this, but they're probably imaginary solutions. They're out in the complex plane, and so we don't see them on the real numbers crossed with the real numbers, Even though when we draw complex numbers, we draw it in a plane that looks a lot like this, it really is representing different things. And this is the real numbers crossed with the real numbers again, and just comparing two sets of them. And so when we see that there's supposed to be two solutions, but they're not actually making zeros happen here, we'll probably just conclude that we're dealing with complex solutions or something else weird like that. And so, so there's another issue. One other thing we run into, guys, is sometimes we'll say, well, if I had like y equals x minus 3 squared. There's another weird issue where we'll run into this thing where this is supposed to have two answers too, because if I FOIL it out, it's got an x squared in it. This is x squared, minus 6x plus 9, I guess, if I FOIL it out. So it's got the x squared in there for sure. I should have two answers, but I don't. When I graph it, I just have two zeros here. One zero. I only have 1 0. And so it's weird, and I got to figure out what that means. But it essentially means, remember, in factored form, this is x minus 3 squared, as we already know. That's x minus 3 and x minus 3. It means it does have two zeros to it. They just are both the same thing. This is 3 minus 3 and 3 minus 3. They're both where we hit the x line. And so our zeros are both at positive 3. And so it's what we say the zeros are, well, it has a 0 of 3 with a multiplicity of 2, like we may have mentioned before. Anyway, this is some of the weirder graphing aspects of it all. One thing that I will say, though, and the only other weird result you'll need to know about it is this. If we have a complex root where, say, instead of it being like 1 or 2 or 3 or 5/8 or something nice, if we get a complex root where we have a square root of a negative in there, like if you did the quadratic formula and it was a square root of a negative, in that case, we would say, well, there's a handy theorem. If I have one that's like all weird, radical 3i or something, 1 plus radical 3i, if that ends up being a root, then guess what also does its conjugate become a root? It's minus radical 3i is also going to be a root. And so we have this given that, not that that's obvious, but this is one of our results that we got in the algebras here, is to say that if I have complex roots, they come in pairs. If I can find one of them, then the other one will come with it. And that kind of comes naturally from the quadratic formula stuff anyway. Nonetheless, okay, so finally, after wasting 5 minutes, I wanted to give you my take on the last couple of these things. Check this out. So find all zeros of this one. Say on number 20, we have 4x to the 3, 12x2, negative 34x plus 30. And then we got to find the zeros best that we can. And so remember, just from like the last section, we'll do our best guess at trying to find things to narrow this down. So if I'm looking at the 30 and at the 4, I'll start by guessing my way in there with things that go into 30 on top over things that go into 4 and a plus and minus version of that. Don't actually write, I guess 30 over 4 could be one of them. But then I'm going to put arrows here to indicate that we're actually looking for a list of things. So things that go into 30 would be like 1 or 2 goes into 30, and so does 3 and 5 and 6. A lot of stuff goes into 30. 10, right? 15 and 30. There's a ton of things that go into 30. And then things that go into 4, fortunately, are not that many. It's just 1, 2, and 4 that go into 4. And then there's a plus or minus version of each one of these things. So these are the things that, as far as what we call rational roots go, are worth guessing. And so, let's see here. And there's some redundancy in here, too, of course. If you see 2 over 2, that's the same thing as 1 over 1, you know. So there's a little bit of repeat, but not much. Anyway, so if I were to try and figure out, like, what are good things to guess here, to find a first root, shoot, probably I'd start with with whole numbers, maybe even positive whole numbers. And so I'd say, well, let's try 1 over 1 is just 1. Or I could try 1, or I could try -1. And then we could do 2 over 1, and 3 over 1, and 5 over 1, 6 over 1. All of those are probably worth trying. So plus or -1, plus or -2, plus or -3, plus or -5, etc. These are probably what I would start with because they're whole numbers and they're easier to deal with, whether you be plugging them in or doing synthetic division or whatever. That's what I'd recommend. So let's try that out and remember how this goes. So we have, I'll try, let's see if we tried -1, we'll say, and then we'll try +1 and then whatever until we get one that works. And so let's see here. If I were to try -1, -1, and I do the synthetic division thing. How did the function go? It was 4, 12, 34, 30. Okay, so we have 4, 12, 34, 30, and I think the 34 was negative, yeah. 4, 12, negative 34, 30. So we'll drop the 4, and then we'll times it, so that's -4. Drop there, so plus that, it's 8, and then times it's -8, plus that, what the heck is that going to be? -42 times -1 is +42. And then finally we have a remainder, and it's 72. But remember, that's key. If it comes out with a remainder, then we need to try something else. And so we'll say trying a remainder, that means -1 is not a root. So we'll try +1, see if that's a root. +1, or a 0 or whatever, sorry. I always use the terminology wrong. Anyway, so dropping the 4, we have 4, and then times 1 is 4, 12, 16, times the 1 is, I like the 1 thing, because timesing it is so easy. And then -34 plus 16 is like -18, I believe. Shoot, did I mess that up? Let's see. Let me think about that for a second. I feel like I messed it up. I paused it and thought about it for a second, and I did not mess it up. I don't know. I don't think so anyway. So then -18, shoot, that's going to make whatever that is. It's not 0, though. It's 12 or something, right? And so we'll say 12. We'll assume that it's 12. I don't know. Anyway, so that means 1's not it because this remainder is not 0. We got a remainder out of it. So then try and try and try. And so you're trying a bunch of stuff. Fortunately, by the time you do a bunch of these, this part goes really fast, as long as Adam's not yapping through it, you know. Having looked at this a little bit, maybe I'll skip to the end so to not bore you. I think that 5 or -5 comes out as one of them. Yeah, it looks like -5 should work. And so if we do, after you try a bunch of these, -5 looks like I think it'll work for our first rational root. Let's make sure. So we have 4, 12, -34, +30. Let's try. Regular 4. Then timesing that's -20, plus the 12 is -8. Timesing that by 5, that's double negative, so +40, 34 and 40. That makes a +6 if I add those together, -34 plus the 40, and then 5 times 6 negative is -30. Indeed, it worked. We have a 0 remainder. This is beautiful. So -5 is one of our roots. And so we'll say, we don't have to do anything with that. We don't have to put this thing in factored form or anything. We'll just say -5 found one. And then we'll remember how to use the rest. Now that I found one, the remainder here, since that was x to the 3 before, remember that was a 4x3 that we had, and I divided out an x value, or an x, essentially this is equivalent to dividing out x plus 5, if you might remember from the last section. This is like 4x squared minus 8x plus 6. Now we have a new smaller polynomial, and we just have to figure out the zeros of that. And so from there we have 4x squared plus 8x plus 6. Oh, you can't even see it. Minus 8x plus 6. And we're wondering, well, what do I got to do to make this equal 0 now? Because those will give me the other two zeros of the function if I just get the zeros of this part, because now I found the 0 of the first part. And so it's getting a little bit fuzzy down there. Come on, focus, focus. Do it. Does that look as out of focus to you as it does to me? There we go. So from here, we got to figure that out, and I don't think this is going to factor real well, and that's where we run the risk of getting complex roots, because the answers are getting funny now, you know. Nothing goes into 24 that adds up to 8 that I can think of. I don't know, maybe it'll work, but whatever. So we'll just try it by the old quadratic formula and see how it goes. X equals negative b would be a minus 8, so that's positive 8 plus or minus square root. B squared would be negative 8 squared minus 4 times a times c is 4 times 4 times 6 over, all over, that is 2a, so 2 times 4. Cleaning that up a little bit, we have an 8 plus or minus radical on the outside, and then it's all over. 2 times 4 is 8 on the bottom. And then let's clean up the square root here. Negative 8, oh, squared? It's not really a star if I catch it before you say anything, and I couldn't hear you. So 64, and then that's a positive 6 in there, right? Yeah, don't let that look like a negative 6. Anyway, so that's 64, and 4 times 4 times 6, that's 16 times 6, or 24 times 4. Okay, 24 times 4, if I do it that way, that's the same thing as 12 times 8, so that'd be 96. So this is 64, take away 96. That's going to be like 30-something, 32 negative, I think, negative 32. And that's where we get imaginary solutions coming up. So right off, I can see this is a square root of a negative, and then we're going to clean it up, and then we'll say that we found our other two roots. So if we clean this up, let's see how that looks. Put the I on the outside to take care of the negative, so it's radical 32i, but also we got these 8's sitting here, and then the 32, well, that'll pair out, if you will. So 32, by the time I break it up, it's 2 times 16, which is 2 times, or you could do 4 times 8 or whatever you like. By the time it's all done, that's 5 2's. And so that's a pair of 2's, a pair of 2's, and a 2 left over. So a pair of 2's becomes a 2 outside, a pair of 2's is a 2 outside, so that's 2 times 2 on the outside, or 4 on the outside, radical 2 on the inside, with an I sitting there. And then we have ourselves almost done. Since all three of these can reduce, then we'll reduce all three of them. 4 goes into both, or into all of them, so 4 into 8 goes 2 times, plus or minus 1 radical 2i, so that's just a 1 radical 2, or you can just put radical 2 because you don't need the 1, and then 4 goes into 8 2 times again. And now we have essentially both of our other complex roots, because remember they come in conjugate pairs, and we kind of, that becomes somewhat obvious to us when we do this by quadratic formula, because we have the plus and the minus version of it. So our other two roots are, besides the 5, it's this. We have, oh, I guess I should clean that up. Okay, so to put that in a plus bi form, we'll split the fraction into two parts. So I'll put the 2 under each part. So that's 2 over 2. And then I should have split that. Pretend like I could scribble. There we go. Plus or minus, and then it's a 2i, or radical 2i, also over 2 as two different fractions, and then we'll reduce them what we can. 2 over 2 reduces, that's 1. Plus or minus, that's not going to get any better, so radical 2 over 2i. That's looking pretty good. And so then we'll just say that, I guess. We got ourselves two complex solutions. One of them is the plus version, the other is the minus version. So we'll say negative 5 was the real number, and then we have negative 1 minus radical 2 halves I. That's another one. And then negative 1 plus radical 2 halves I. Those were our three roots. For some reason, that one got circled. I don't know. Anyway.